Hello. Today we start a new chapter in our statistics talks, which is about statistical hypothesis testing, mostly about a null hypothesis and p-values. This is how it works. There is an experiment using equipment and protocols I don't understand, and then there is some statistics that you don't understand. And at the end of this process, of this collaboration, there is a p-value. And if p-value is less than 5%, well, then everybody is happy and we can publish a paper, right? Not right. It's not that simple. Misunderstanding and misusing p-values led to lots of problems, as you can see from this headline. It's a paper published a few years ago, another one which talks about irreproducible results, and probably the most famous one published quite a while ago, why most published research findings are false. This is all related to p-values, misunderstanding and abuse of p-values, and yet p-values are at the heart of scientific research. You use them every day. You make and report scientific discoveries based on p-values. Hence, it's imperative that biologists understand p-values and statistical testing. And that's what I'm trying to teach you today and in the next few lectures. Let's start with the basics. Null hypothesis. What is a null hypothesis? Null hypothesis is a default position. We denote it as H naught, and we usually say that there is no effect, no change between two biological conditions, no change between control and treatment. There is no difference, there is no effect. And then we search for evidence against this null hypothesis. And if we find evidence which is strong enough, we can reject the H naught and we can say, oh yes, we found an effect. Otherwise, our position remains unchanged. We don't prove anything. We just stay where we were and our default, there is no effect. There is a nice analogy to a court trial where the default position in the beginning is that the defendant is innocent. And then we search for evidence against this innocence. And if we find strong evidence, we can then declare the defendant guilty. Otherwise, our default position remains innocent. Innocent until proved guilty beyond a reasonable doubt. By the way, you cannot prove the null hypothesis, just like you cannot prove innocence. How do we look for evidence against our null hypothesis? Well, we do an experiment as usual, and we collect data. Imagine that you have two samples of mice, 12 English mice and 9 Scottish mice. Yes, there are no Scottish or English mice, really. This is just a parable, but you have two groups of mice and you weigh them and you measure body mass of each of them, and the result is presented in this plot. The mean mass of English mice is 19.0 grams, while the mean body mass of Scottish mice is 24.0 grams. Hence, the difference between these means is 5 grams. Now, there are two possibilities. Either the difference is real and Scottish mice are truly heavier than the English mice, or this is a fluke and the two samples come from the same population of mice and the observed difference is obtained by chance. What are the chances of having this fluke, of having this large body mass difference purely by chance? Well, we can do another Gedanken experiment, and we do it under the null hypothesis, which means that we assume in this experiment that the null hypothesis is true. There are no English mice, there are no Scottish mice, there is just one population of British mice. with a mean body weight of 20 grams and standard deviation of 5 grams. What we do now, we select randomly 2 samples of mice from this British population. One sample size 12 and one sample size 9, exactly like in our original experiment. We measure the body weight, find the mean, and find the difference between the means between these 2 samples. And then we repeat it multiple times, let's say 1 million times. It's possible to do it in a simulation, and we build the distribution of the difference of the mean mass, delta M. If you perform such a Gedanken experiment in a computer, this is what you get. This is our result under the null hypothesis. I have to say it again. This means that we assumed that the null hypothesis is true. So in this experiment, we know the null hypothesis is true. The distribution here represents all 1 million simulated results. And more likely results are here in the middle, where the body mass difference is small, and less likely results are at the tails, where the body mass difference is larger. And now you can guess what happens next. We look at our actual observation, and if you remember, the observation told us that the difference between mean body mass was 5 grams, and put it in the context of all simulated results. And it turns out that 12,453 of the simulated results, or 1.2% of simulated results, have larger mass difference than in our actual experiment. And this is our p-value, which is a probability of getting the observed or more extreme result by chance under the null hypothesis. Let's summarize this. What's the relation between null hypothesis and p-value? If, and that's a big if both samples were taken from the same population, and this is the null hypothesis, and on the right, there is a graphical representation of the null hypothesis, then the probability of observing the difference in mean body mass of 5 grams or more, which is marked here, by chance, due to random sampling, that's the only reason we can get these random results. This probability will be 1.2%. And this is the p-value. This is this tail probability marked with a dark shaded area. In other words, we can say that we observe an effect, the 5 gram effect, but it will occur by chance, purely by chance, in 1.2% of repeated experiments, which is about 1 in 80, which means you have a 1.2% chance of making a fool of yourself if you publish this result. This is the definition of p-value I really like. P-value is the probability of making a fool of yourself. Why do we use more extreme? Well, first of all, we cannot cut off probability of x equals 5 is 0, as you know. It has to be a tail probability. We look at all results which are the same or even more extreme than our actual result. And if we have the null hypothesis and we have a p-value, what do we do with this? We reject it or what? Well, our default position is h0. This is our null hypothesis. It also includes all other additional assumptions. Some of them might be implicit. There will be assumptions about the quality of your experiment, that all the biology is correct, that there are no technical issues. There's lots of stuff here. There are lots of hidden assumptions, apart from your null hypothesis that there is no effect. And when you look for strong evidence against this, and if there is not enough strong evidence, well, there is no result. First of all, absence of evidence is not evidence of absence. So you can't prove a null hypothesis. You can't say, we proved that there is no difference, that there is no effect. Perhaps evidence is too weak. Perhaps your experiment is underpowered. There is really nothing you can tell. On the other hand, when you have strong evidence, you can reject the null hypothesis. And then you can say that perhaps data are incompatible with H0 and we actually observe the effect, or data are incompatible with any other of your assumptions because maybe something went wrong with the experiment. Maybe you are looking at a batch effect or something else. So you reject H0 at your own risk. As I said, you cannot confirm the null hypothesis, and this is the example that shows you why. This is a result of a large-scale gene differential expression experiment, which was done in yeast in two conditions. There was a wild type and a mutant. The experiment was done in 40 replicates, and having all these data and doing the differential expression, which essentially assigns p-values to each gene and tells you whether this gene changes or not. If we can use then sub-sample of the original samples. Instead of full 40 replicates, we can use, for example, two. Randomly select two replicates from each condition, repeat this many times, and find how many significant changing genes this software discovered. And as you can see, we typically discover about 20% of genes. That means if you have two replicates, you will discover 20% of genes that disagree with H0 or they reject H0. But that doesn't mean that the remaining 80% of genes do not change. Because if you do this experiment in 16 replicates, then 60% of genes disagree with H0. With increasing number of replicates, we increase sensitivity of the experiment and discover more and more changing genes, but we cannot say anything about the remaining genes. If your p-value is greater than an assumed limit, you cannot say that there is no effect. That would be an incorrect conclusion. You can only say that you have insufficient evidence to make any conclusions. You cannot prove the null hypothesis. Remember, this is very important. This slide shows the workflow of statistical testing. You start with a statistical model, which you are going to use for your testing. That will be a specific statistical test. You formulate your null hypothesis. Usually you say there is no effect. You have all other assumptions. You assume a significance level of, let's say, 5%. Then you do your experiment and collect data. And once you have done it, you can perform a statistical test against the null hypothesis. And as you will see later, in most cases, it involves finding a tail probability in a certain distribution. And this is our p-value, probability that the observed effect is random under the null hypothesis. If p-value is less than our assumed significance level, you reject the H0 at your own risk and you claim effect is real. If p-value is greater than alpha, on the other hand, you can only say that there is insufficient evidence. Let's focus on that one particular statistical test, which is called Fischer's exact test. I'm going to tell you a story. The story begins at Rothmanstedt Experimental Station in Hertfordshire in 1920s. Ronald Fischer, the gentleman on the left, was appointed there as a statistician, and his job was to help biologists to make better crops. And one afternoon, a few scientists, including Fischer, gathered for tea, as they used to do in those days. And Fischer offered a cup of tea to his colleague, Muriel Bristol, who was sitting beside him. And she said, no, I would really prefer if you poured milk first and then tea, because she noticed that he poured tea first and milk later. And to that, Fischer answered, well, surely that doesn't make any difference, that the taste at the end will be exactly the same. But Miss Bristol was adamant that she can tell the difference whether the tea was poured first or milk was poured first. Fischer, being a statistician, decided to check Miss Bristol's claims and devised a simple statistical test. This is what he did. He made her 8 cups of tea, 4 of which had tea and another 4 had milk poured first. And then he presented her these cups in a random order. And Miss Bristol was supposed to tell for each cup if milk or tea was poured first. And I will tell you how Ms. Bristol performed in a moment. To summarize, the null hypothesis is Ms. Bristol has absolutely no clue what she is doing. And to explain this, we do this little experiment here. Imagine you have an urn with white and black bowls. These colors could represent cases where tea was poured first or milk was poured first, or it could represent any biological condition in your experiment. It is just easier to visualize it and explain the Fischer's test this way. What you do now, you draw a certain number of balls, like 5, without replacement. That means you take a ball out of an urn and leave it outside. It also means that removing balls changes the probability. It changes the ratio between white and black balls here in the urn. Our question now is as follows. What is the probability of finding exactly k white balls? And to answer this, well, first I have to introduce binomial coefficient. You might be familiar with this. If not, it's represented like this, n choose k. This is in brackets n over k, but we read it n choose k. And it's given by this formula. Exclamation marks denotes factorial. Factorial is a product from 1 to n, so it's 1 times 2 times 3 times 4 up to n. And in combinatorics, this is the number of possible k element subsets of an n element set. It's easy to explain it in an example. On the right here, you have a set of 5 elements. There are 5 numbers, 1, 2, 3, 4, and 5. How many 3 element subsets are possible? And this formula, 5 choose 3, you put all the numbers in and you will get 10. That means there are 10 possible 3 element subsets from a 5 element set, and they are shown here. They are all 10 possibilities. Using this formula, you can find the number of possible subsets. And to answer our question about the probability of getting exactly k white balls, we need to count all possibilities. This is what Fischer's test is about. It counts all possibilities. In this example, we have 5 balls and we draw 3 of them and we ask, what is the probability of getting exactly 2 white balls? First, let us count all possible combinations. We select 3 balls out of 5. So 5 choose 3. There are 10 possible combinations of 3 balls out of 5. This is our universe, all possible combinations. Now we want to find how many of them are favorable in our situation. That means they contain exactly 2 white balls. And to do this, we first look at white balls. There are 3 of them, and we need 2. That means 3 choose 2. There are 3 possibilities of finding 2 white balls out of 3. And they are shown here. It's 1, 2, 1, 3, and 2, 3. And the remaining ball, this one, has to be black. So there are 2 choose 1. There is only 1 ball that we choose. There are 2 possibilities of finding 1 ball out of 2. And they are shown here. It's very simple. It's ball 4 and 5. We have 3 possibilities here, 2 possibilities here. And to find all favorite combinations, we need to multiply these numbers because all possible combinations are like this: 1, 2 times and 4, 1, 2, and 5, 1, 3, 4, 1, 3, 5, 2, 3, 4, 2, 3, 5. We multiply this number of combinations by this number of combinations, and we find that there are 6 favorable combinations. There are 6 combinations where we have exactly 2 white balls, and there are 10 combinations in total. Hence, the probability of finding exactly 2 white balls is 60%. It's 6 divided by 10. And here we come to something which is called hypergeometric probability. Have a look at this bigger example where we have 36 balls, 20 of them are white, and 10 balls are drawn. And we want to know the probability of finding exactly 8 white balls. We use the same formula as before. Here are combinations with 8 whites, and here are all possible combinations. And these numbers, if your counts are larger, these numbers get very, very large very quickly. You can see here there are over 254 million possible combinations, possible selections of 10 balls out of 36. And from this, we built something which is called a contingency table, and it's shown here. Columns of a contingency table usually correspond to experimental conditions, and they should encompass all possibilities. In our case, the condition is the ball is either drawn or the ball is not drawn, it remains in the box. Rows typically correspond to the outcome of an experiment. In this case, the ball drawn is either white or black. And the table itself contains counts in each of this category. Our data are here on the left. The contingency table here, the white part, this is the core of the contingency table. It contains all the counts. Blue shaded areas show the sums. This is the total number of white balls, total number of black balls, total drawn, total not drawn, and this is the ground total of all balls. And sometimes it depends how you perform your experiment. You don't know all the numbers here within the white box, but you know the sums. And in this case, our data are here. We have 36 balls in total. That means our ground total is here, 36. 20 of them are white. That means that the sum of this row is 20. And 10 balls are drawn. That means the sum of this column is 10. We have these 4 numbers which are marked in black and bold, and the rest can be calculated from them by subtracting. So we can find all the numbers, and our contingency table here is the white bit. It's this 8, 12 to 14. This is what we use for the test. And the contingency table contains counts in each category. Now we can do the same for different values of K. This is more abstract notation. We have K here, the number of white balls drawn. There are all the marginal sums, and there are formulas for particular values here. And now we can cycle K from 0, 1, 2, and as we do, we change all these numbers because the sums are the same, and we get a sequence of contingency tables, and they are shown here. And for each of them, we can find a probability. The first one had a K of 0, and probability of finding 0 white balls is this, is very small. This is K of 1, and adjusted other numbers. This is K of 2, up to 10, K of 10. And from this, we can present these numbers, these probabilities, as a probability distribution. This is called hypergeometric distribution. And that shows you what is the probability of finding this number of white balls in a draw. In statistical hypothesis testing, we always look at a tail distribution because p-value is the probability of finding observed or more extreme result by chance. Since we have entire probability distribution here, we can now answer the question, what is the probability of drawing 8 or more white balls? This is a tail probability, and we can find it simply by adding these 3 probabilities, which we already know. We calculated them, and the sum is 0.071 here, 7.1%. This is what is called enrichment. Do we have more counts than by random? We could perform a left-sided test, which will be a test for depletion. Do we have fewer than random? Or we can perform a two-sided test. Is our result different than the random result? At the bottom here, I show you a couple of examples how to deal with hypergeometric distribution in R. As usual, there is a D hyper for density, which calculates individual probabilities, and P hyper, which is the cumulative distribution. These numbers are a bit complicated. You can check help for D hyper and find what they are. They are not the contingency table. Some of them are sums. But there is a much easier and better way of performing Fischer's test. So don't worry about this too much right now. Okay, we played with the balls. We can now get back to Miss Bristol. She was served 4 cups where milk was poured first and 4 cups where tea was poured first. And this is how she performed. That was her answers. Where milk was first, she guessed correctly 3 times, and once she made a mistake. And the same here, where tea was first, she guessed 3 times correctly and made one mistake. Now we can put it in a contingency table. The experimental conditions here are tea poured first. This is the first column, and milk poured first. This is the second column. The outcome of the experiment is what Miss Bristow said. When tea was poured first, she guessed correctly 3 times and made one mistake. When milk was poured first, she guessed correctly here 3 times and made one mistake. This is our contingency table. We can also have over sums. And the one-sided probability of getting this or more extreme result by chance is the sum of these 2 bars in this probability distribution, which is 0.24. This is the p-value of this test, and this is the probability of obtaining 3 or more correct answers by chance. And because p-value is large, the null hypothesis cannot be rejected. So we cannot make really any conclusion. We have insufficient data, and by looking at these numbers, I can tell you that this experiment is seriously underpowered. To make a good experiment with good conclusions, you would need many more cups of tea. The contingency table in general is a table with counts like this. Columns typically are our input. Our treatments could be treatment 1, treatment 2, control treatment, could be wild type and knockout, whatever you put in the experiment. And rows are typically a result, success or failure, whether a patient responded to treatment or not. You can swap them around, it doesn't matter. I'm going to use it this way. That will be our input, that will be our output, and we have counts in each category. Why is it called contingency table? Contingency means association, and we are testing for association between experimental conditions and the experimental result. There are 2 interpretations of Fischer's test. Interpretation 1, it's a test of independence. And the more generic null hypothesis in this test is that variables are independent. And in case of Miss Bristol, would mean that her answers do not depend on whether she got milk or tea first. That means that her answers are random. This is an example of a larger experiment with 12 cups of tea. This is what she was presented with: tea first, milk first, tea first, and so on. And these are her answers. And you can look at this and you can immediately see that there is very little relation between these 2 variables. They are independent. Her answers do not depend on what tea was served. Put these numbers, counts in the contingency table, and you find a p-value of 0.58, about 60%. We do not reject the null hypothesis that these variables are independent. The second example here is different. You can see immediately that Ms. Bristol's answers are very similar in most cases to the actual tea. Occasionally she can make a mistake, but in most cases she gives a correct result. That means that these 2 variables, tea served and her answer, are highly correlated. They are dependent on each other. You put these numbers into a contingency table and you get a p-value of 0.03. If we set a significance level at 5%, we can now reject the null hypothesis and claim Ms. Bristol's answer follow what she was given and she knows what she's doing. The second interpretation is that it is a test of proportion. And the null hypothesis is that proportions are the same in each column, or alternatively proportions are the same in each row. You can swap columns and rows in the contingency table. It makes absolutely no difference. This is our first extended experiment where her answers were completely random. And you can now put these things in a contingency table and you can find proportions in each of the columns, which means the proportion of counts in the first column is 4:2. It's here. And the proportion in the second column is 5:1. And these two proportions are, well, they are different, but because counts are small, they are not statistically significantly different. And they are visualized here in this plot. This plot shows counts in the contingency table, and you can see the proportions by comparing bars in the same category. This is our first column, T first, and these are the answers, 4 and 2. And this is our second category, milk first, and there are answers. And this proportion is not very much different from this proportion. It's much more evident in the second case, where the proportions are 5 to 0 and 2 to 5. And in this plot, you can see that this proportion is much different than this one. They go the other way around. This is the test of proportion. And in this particular case, p-value is small, and we reject the null hypothesis that proportions are the same in each column. They are different. An important application of the Fischer's test is enrichment analysis. When we ask if a given selection of objects, for example, genes, is more likely to have a certain property than a random selection. This example shows a set of genes, and some of these genes are annotated with a Go term. For those of you who do not know what Go terms are annotations, functional annotations, and many genes have multiple annotations related to the function. And in this case, we have several genes which are annotated with this Go term, regulation of DNA replication initiation. That means these are genes that are involved in this process. Now imagine you perform an experiment in which you do differential expression between two conditions, for example, wild type and a knockout. And you want to find out whether these changing genes are preferentially annotated by this Go term, or in other words, they are functionally enriched. The question is our Go term more frequent in the selection than in a random selection? Or in other words, is this Go term enriched? And we can do it using a contingency table and Fischer's test. These are results from an actual experiment. We had 668 genes in total. So we put a ground total here of 668. 7 of these genes, of over genes, were annotated with this particular Go term. This is the total, all the genes with a Go term. 44 genes are differentially expressed. This is our selection. So this column shows all differentially expressed genes, and there are 44 of them. And 6 of these differentially expressed genes have this particular Go term. So we put 6 here. We can fill all the numbers, all the remaining numbers, and then we can perform a hypergeometric test now. And the question is, what is the probability of finding 6 or more genes with this particular Go term in our selection? And this probability of x being greater or equal to 6 is very low. It's about 10 to minus 7. You can use a p-hyper function to find this. That is an easier way. I will show you in a second. Absolute numbers are very important in contingency tables and Fischer's test. Consider a report in a newspaper where they report the clinical test results of a new cancer drug, and they say, oh, 15 patients treated with drug A survived, while 30% of patients treated with drug B survived. Excellent. Drug B is 100% better than drug A. That will be typical reporting in a newspaper. However, you miss a very important thing. You miss actual numbers here. Imagine this is the numbers in this experiment, where the totals were 20 patients treated with drug A and 10 patients treated with drug B. These are the proportions, 15 and 30%. You put all these numbers in the contingency table, and if you perform a two-sided test, we are just interested with whether drug A and B are different. The p-value is 0.37. We cannot reject the null hypothesis. This experiment is underpowered. We simply do not have enough counts. If you do the same experiment with 80 and 100 patients and the proportions are the same, so proportions here and there are exactly the same, 15 and 30%, but counts here are larger. And this test will give you a p-value of 0.02, 2%. So there are two morals out of this. The first one, do not trust newspapers when it comes to data and statistics. And moral 2 is that estimate the required size of your sample before you do the experiment. This is called power analysis, and you need to do this before you perform experiment with animals, for example. Oh, and one thing, unfortunately, I saw some people do this. Never ever use percentages in Fischer's test. Contingency table contains counts, and it's very important that these are actual counts, not percentages. Don't do this. This is the summary of Fischer's exact test. The input for the test is 2x2 contingency table. Actually, larger tables are also possible, but we focus on tables 2x2. Typically, columns are your treatments, your conditions, and rows are outcomes of the experiment. The table contains counts, that's important, and counts of subjects falling into categories. The usage of this test is to examine if there is an association, or in other words, contingency between two variables, whether the proportions in one variable depend on the proportions in the other variable, or if there is an enrichment. The null hypothesis is that proportions in one variable do not depend on the proportions in the other variable. These variables are independent. And a few comments. This is the exact test, as the name suggests. It counts all possible combinations. Other tests are sometimes an approximation. You use this test when you have small numbers. It's very good for small numbers. For larger numbers of hundreds, if your counts in your table are hundreds, you should probably use chi-square test instead. I will explain it in the next lecture. And you should carefully choose between one and two-sided tests depending on what your question is. How do you do this in R? I showed you that you can calculate using a hypergeometric probability function, but fortunately there is an easier way of doing this. There is a function called Fischer.test, and the input for this is a contingency table. This is how you can create a little matrix like this in R. You bind two rows. R bind is binding rows. The first row is 3 and 1. It's the first row. And the second row is 1 and 3. And you create this little matrix. This is our contingency table. So this is an example of t-testing with this Bristol. And you specified what alternative is, whether it's one-sided test, greater, less, or two-sided test. And when you do this, it gives you lots of information, including a p-value of 0.24. And this is the example of our Go enrichment. This is the contingency table for the Go enrichment, and the result is here. P-value is very small. Thank you. That's everything for today.